Good morning, everyone. Thank you for being here. So it's very good to be in Cargèse again. So thank you, Matthias, and thanks the organizers, Romain, Sébastien, and Fabrice. I'm very happy to be in front of you this morning. So as Robin said, now I have a double affiliation. So I share my time between the Langevin Institute at ESPCI Paris and the Institut d'Optique in Paris-Saclay. So two very nice places. So today, the topic of the lecture is about the impact of partial order that I will define, okay, on scattering and absorption. So before I really start, I need to acknowledge the many people who actually did the works I'm going to go through, and also many other people. You know, your knowledge on the field depends a lot of many interactions you can have with a large bunch of people, and places like that are very good for this. So I'm not sure I could list everybody here, but these are the people at Langevin who actually worked. So Romain Pierrat, that everybody knows here. So Romain Pierrat is not only one of the organizers, but he's a very good physicist, deeply involved in many topics. And these are the list of PhD students or postdocs who, along the years, have been involved with us in this topic. These are external collaborators with whom we actually worked on some of the parts I will develop later. And again, the many important people from which I've learned a lot on this topic. So to give you a flavor of the story I'm going to tell, so these are 4 examples of the appearance of blue color. So this one is paint, so this is color due to absorption. This blue color here is obviously, as you know, due to scattering. I'll come back to that in a minute. And these are 2 other examples of blue color that, again, I will come back to this, that here has to do with the fact that you get diffuse light that is mostly reflected at a given wavelength due to the fact that the underlying structure in the feathers of this bird, you know that this is typically 1 micron, so as you see, this is a strongly correlated structure, and this partial order has to do with the fact that you can have blue reflection with diffuse light. And this other example here is on the nanoscale. Here what you get actually is the blue color you see when you shine light, white light, on a structure that is gold. So the black color here is gold deposited on glass and close to percolation. So this is 50 nanometers here, okay? So it's really a nanostructure surface. What you get is a strong absorption in the red and near infrared that is responsible for the appearance of this blue color. So it's not easy to understand what really happens here, okay? But what you get actually is a mixture between absorption and partial order and also internal resonances in the metal that gives you this very nice blue color of gold. So this is the outline. So I will start with really basic fundamentals of light scattering, insisting on some aspects that sometimes are forgotten, and this idea that actually special correlations between fluctuations in a disordered system are actually the root of scattering. So talking about scattering without talking about special correlation and partial order is a bit contradictory in the end. So I will say a bit more about this in a few minutes. Then I will discuss a special case of partial order, that is the so-called hyperuniformity, and comment about some of the consequences. This is a very active topic currently. Then I will say something about the way you can make partially ordered materials for photonic in practice, and show you also some examples of current works in this direction. And the last part, I will discuss the fact that you can also play with absorption. Sometimes when we deal with multiple scattering of light, we want to absolutely to avoid absorption, but sometimes it can be useful to increase absorption, and I will show you also recent works. And if I have time, if this thing is not too red at the end, maybe I will show you some applications that we're working on that have to do with radiative cooling. So this you probably all know in this audience, that if you send a beam of light in a scattering medium or any kind of wave, then you have the attenuation of the incident beam. In the direction of the incident beam, you have exponential attenuation. And this attenuation is described by this extinction mean free path that, in the most general case, mixes scattering and absorption. And the light that is taken from this ballistic beam by scattering is distributed around and create the diffuse intensity that you know when you go deeply in a scattering medium. So this lecture basically has to do with the influence on those mean free paths of partial order and some consequences of that. So partial order, what we mean by that is the fact that if you take, for example, here two-dimensional distributions of points, so on the left, the points are distributed completely randomly, so like the molecules in an ideal gas. And from left to right, little by little, you impose some correlations, some statistical correlations between the positions of two different points. And so it's obvious, I guess, that when you move from left to right, you see that little by little, you have more and more order. Although even here, it's not crystallized, it's not a perfect crystal, so it's still disordered, but with a high degree of correlations between the positions of the different points. So now, if those different points become scatterers for waves, then the properties of this material, although all the number of points or the number of scatterers and the type of scatterers remains the same from left to right, the properties will become very, very different. And also I will show you that these are not tiny effects. You can completely change the story, even qualitatively, when you induce partial order. So this has been known for a long time. This paper in 1990 is sometimes taken as the first paper, and I think it's right, showing the strong influence of partial correlations in a colloidal suspension. So this was done by Fradon and Maret. By the way, Georg Maret is not here, but for people, let's say, middle old people like me, who've been here, my first step in this community was 98 in Les Houches and 99 here, okay? When you go through the literature in this field of light in complex media, I must say that you find several papers that are first papers by Georg Maret. I think he's the first one who really showed this influence of correlation. So what you see here is a colloidal suspension, and when you make the volume fraction larger and larger, so this is the inverse of the mean free path, so this is the scattering strength. This is what you would get for a non-interacting suspension with particles independent from one another, and then you start to get hard sphere interactions, and you change the story. Okay, so this is the first paper that shows that. I'll come back to that. But Georg Maret was also the first to introduce the concept of dynamic light scattering in the multiple scattering regime. I think he's also the first that has shown, Claude, correct me if I'm wrong, but acousto-optics in multiple scattering media. He has a very fundamental experiment, and so on. So I just wanted to say that because you have people that have really had a very, very important contribution to the field. You have another evidence, also I will come back to that a bit more later, but in nature, actually you have colors that can appear that are not due to absorption, but that are due to selective scattering. So these are examples of birds where the blue color actually is due to the presence. So these are microscopic pictures of the structure you have in the feathers. So this bar here is 1 micron. So this is a work done in collaboration between different groups in Yale, including Roy Sauk, who is here. And this is very interesting to understand not only the connection between those highly correlated structures and the appearance of color, but also how nature produces such structure in vivo, which is also a very fundamental issue for people working in soft matter, and also the why evolution produces this. And Richard Prum is someone who introduced this idea, this connection between the physical, chemical properties of those things, the light scattering problem, and the evolution, which is also a very interesting topic. And I also want to stress some work in the group of Silvia Vignolini in Cambridge. So she has been working a lot also in understanding how you find, not only in animals but also in plants, structure that, thanks to correlations, completely change the scattering, the story of scattering. So here, this is this famous blue beetle, which is so far, if I'm correct, I think this is the most strongly scattering material found so far in nature, with a mean free path on the order of 1 micron, if I remember correctly. So this is very interesting to see that you can produce things that are not easy so far to produce in the lab. So now I was telling that if you have now, let's assume that this now is a material. Okay, so I will speak about idealized material. Okay, so let's assume that it's just a distribution of two-dimensional scatterers in a transparent matrix. So if the positions are completely independent, like in an ideal gas, so what you know is that the scattering mean free path. So for the independent structure, so in terms of particles are independent from one another, sometimes we call it the Boltzmann mean free path, which is our reference. So the mean free path is simply the product of the number density. So rho is the number of points per unit surface here, and sigma s is the scattering cross-section of one particle. But now, if you induce partial order, then you will enter this topic of correlated scattering, and things will become different. So I will describe that in the next slides. But basically, the idea is that even when you compute the average intensity, now the interferences between the field scattered by the different scatterers will not be zero, and this will change the scattering or absorption property. So I'm starting with very simple things, but I think it's good to really understand the rules of the connection between the mean free path and the structure of the medium. And to do that, we can start with single scattering. So assume you have a set of individual scatterers, can be 2D, 3D, doesn't matter here. So you send an incident beam, and you look in the far field, the scattered field here, in a given direction. So Ks is the wave vector in the observation direction, and this is the incident wave vector. It's elastic scattering. So the length of those arrows is 2 pi over lambda, lambda being the wavelength in the background medium here, it's single scattering. And I will call Q the difference between those two wave vectors. So if you write the field in a given direction in the far field here, so you have an amplitude, it's a spherical wave in the far field, you have an amplitude, okay, that depends on the incident and observation wave vector. And then you have to sum up the fields scattered by all the individual scatterers, and you have phase differences that you can calculate very easily in the single scattering regime, and Rj are just the position. So you sum up the field scattered by all those particles, and you get the scattered field. You can write it a bit differently if you introduce the number density. Okay, so this is the number density, so the number of particles per unit volume. That's the way it's defined. So you can rewrite this way. Okay, again, this is very, very easy stuff. This is the first lecture of scattering theory here that you probably have in the past. If you plug this into this, you just recover that. Okay. Now let's put some statistics, because we will be interested in the average scattered intensity. So don't forget that what we mean by putting some statistical description is that the observable should be something that is average over many different configurations. For example, if you take this picture of a glass of milk, during the exposure time, particles have moved. So what you see here is an average intensity. Okay. So averaging means that the field, you can write it as an ensemble average plus some fluctuations, with the fluctuation of the field obviously averaging to zero. But the power, so if now you look at the intensity, which is the square modulus of that, the average power, so you square this thing. There's no cross term on average because this is zero. So you have two terms, and really keep in mind that the intensity carried by the average field is what sometimes we call the ballistic beam, which is this beam here that is attenuated. And the fluctuations, although they average to zero, they carry energy. So the power carried by the fluctuations is what we call the diffuse intensity. Okay, and that's the quantity I'm interested in now. So the scattered field, I write it this way. And now I want the power in a given direction on average. So I have to compute this, but here it's delta E. And if you take the previous expression, you end up with this that you probably all know, is the fact that the average intensity has to do with the correlations at two different points of the density fluctuations. This is very simple, but it's very important because sometimes people forget that scattering, on average, is due to density fluctuations. Okay? They are not the scatterers that give you the average power. These are the density fluctuations. So this is. We could even say that this problem was the onset of scattering theory. You probably know that this problem of critical opalescence when you have so this is a liquid here, and at the phase transition, close to the critical point, you see that this liquid becomes, that is here transparent, becomes very, very opaque due to scattering. And this was understood a long time ago, but by bright people, because it was really not easy to understand initially, by the fact that close to the critical point, you have density fluctuation in the fluid that becomes long range. Actually, in theory, they become infinite range. And then you start to get fluctuations, correlations of fluctuations of density in the fluid on sizes that become not negligible compared to the wavelengths. And then you get a lot of scattering. Okay, so that's... Now maybe it seems to be obvious, but this was Einstein in a paper, another very important paper by Einstein, who made the connection between this and the origin of blue sky and explaining that these were really density fluctuations that were the root of scattering and so on and so forth. So I think Einstein also has a contribution in our field. So now, what do we get when we are in this regime of independent scattering? Because very often we say, okay, if it's completely random, then I just sum up the intensities scattered by all the scatterers, and that's the end of the story, which is true, but keep in mind that this results from the fact that you are in a very specific regime where, again, this is the expression where this average intensity finds its origin in spatial correlation between density fluctuations that you can write this way, okay? So this is just the expression of this that you have to compute. In the independent particle case, just like in an ideal gas, you say, okay, two different particles are completely uncorrelated. So you can somehow factorize this, and it's just one line, and you get this. So we need the fluctuation, so you subtract this with this, and you get the correlation of the fluctuation. You plug it here, and you get this result. Okay? Because you have an integral that gives you the volume. The average density times the volume is the number of particles. You get this. Okay? And you say, okay, it's just the incoherent sum of the intensities, but don't forget that the root of scattering are the fluctuations of density. Okay? You need fluctuation of density. If you start the calculation by saying, I have a uniform density, you find that the average intensity is 0. Okay? So again, it might be obvious for many of you, maybe it's not for some other, or maybe you just forgot that. So that's why I wanted to spend a few minutes on this, because it's really important to understand that there would be no light in the sky if in absence of density fluctuations. Okay, so it's wrong. Maybe people learned that a long time ago, but it's wrong to say, okay, all the molecules are Rayleigh scatterers, so they scatter light with a cross section that varies like the fourth power of the frequency, and then I sum up all this and I have the blue color. No, it's wrong. I mean, you first have to say, okay, why do I have scattering? You have scattering because you have density fluctuations. And then it turns out that this obeys this omega to the fourth power law, and then the scattering is stronger in the blue. Okay, but you need both. Okay. So now, how can we describe a correlated set? So it's you can do that with the real space expression, or sometimes it's easier to directly use this one. So I come back to the expression. Again, it's still single scattering of the far field amplitude. This the spherical wave, and this interference term. So this is the Q vector I introduced before. And now I can do the same. So I want to first calculate the power that goes in one direction on average, which is this. Okay, and I just square this, and you see that what appears is this factor here, just the square modulus of that average, which we call the Strutter factor. So it's purely geometric, this quantity. Okay? Rj are just the position of the particles, so you sum over all particles, let's say n particles here. And this term describes the positional correlation between the different scatterers and the way they affect the phase of the scattered field. Okay? That's the Strutter factor that I guess many of you know. So now you can compute the average intensity. So remember that you have to subtract from that the contribution to the average field. Okay? So that's why you get this correction here. So you just make the integral of that, you correct. So what you get is this S of Q corrected by its contribution for forward scattering. Q equals 0 is just, let's say, the contribution of the ballistic contribution. So it's a detail, but the Strutter factor that will appear in all the lecture now is this. So you make this summation, but you correct by this, because this is what enters this formula that gives you the average intensity. And for an uncorrelated set, this guy is 1 for all Q, and then it's 1 here, and the integral of that is the cross-section. You recover the previous expression. Okay? So independent scattering would correspond to S of Q equal 1. Now, how can you compute or introduce a mean free path? So what you can do is you can normalize this average intensity by the incident power per unit surface. And then you can define a cross-section, but that would be a cross-section that accounts for the interferences between the different particles that are now correlated. So let's say it's an average cross-section by particles. So you have to compute this. This is the differential cross-section of one particle, the Strutter factor. So again, in independent scattering, this would be 1, and then the integral of that is by definition this thing. But now you have interferences, so you have to account for this. That changes this cross-section. Then you could define a mean free path, okay? That would just be like this. Sometimes we prefer to work with mean free path than often we prefer to work with mean free path than with an average cross-section per particle. And then you get this. So this is the way you can introduce the change in the scattering mean free path due to correlations here in the single scattering regime. The question is, what happens in the multiple scattering regime? So it's a long story to derive the result in multiple scattering regime, but I will just give you a flavor of how you can do that without plugging any equation. But as you probably know, the nightmare of multiple scattering is that you want to transport a quantity like that. So this is the field correlation function at two different points, and if the points coincide, then this is the average intensity. Okay. So what you have to do is to compute all the possible trajectories. These are scatterers, those white circles, for the electric field. So I just put 2 of them, but you have a lot. And the same for the complex conjugate. And you have to compute all the products and average. So there's no way you can do that analytically. But there is something that, saves the life of theoreticians, which is called the ladder approximation, is that in many practical cases, this scattering mean free path, which is the average distance here between scattering events, is large compared to the wavelength. For example, for biological tissues, people doing biomedical imaging, at 1 micron, the scattering mean free path, lambda 1 micron, the scattering mean free path in tissues is on the order of 100 microns. So wavelengths 1 microns, mean free path 100 microns. This works, okay? Even in white paper, this works. You've heard yesterday about Anderson localization, so it's expected that we could see something when this becomes on the order of the wavelengths, and reaching this on the order of the wavelengths for light is a hard problem. Okay? So if you don't do it on purpose, you don't violate this. Okay? So in practice, this is a very good approximation. So in that case, what you find is that lambda over LS is a small parameter. You have a perturbation theory that I'm not describing, but the result physically is the following. says that now if you transport the field correlation or the intensity from here to here, on average, the only contribution that survive are those for which E and E conjugate follow the same sequence of scatterers. So it's like propagating intensities along all trajectories. So it's a perturbation theory. You can derive that. The physics is that assume that you have two different trajectories for the E star and E that only differ by one scatterer. On average, the path length difference will be on the order of Ls, which is large compared to lambda, so you have a huge phase shift. So in practice, you have all possible phases, more or less with uniform distribution, and then all the cross-term wash out. This is basically the picture you can keep in mind. But this is not the full story for us. Because this works in a medium for which all the position of particles are independent. So now if you have special correlations, you have another term that can contribute, which is the fact that you can have trajectories for E and E star that follow different sequences, but with particles with a non-negligible degree of correlations. And then those trajectories will also survive the averaging process. So in the presence of correlation, you have to compute trajectories like this, and mixtures between them. Okay? And that's the difference between independent scattering and correlated scattering. So that's the way you manage the computation. So it's hard work, but at least when the particles only interact in the far field of each other, I will not enter here the problem of large enough densities for which you have near field interaction, then the result is very similar to what you get for single scattering, but the difference now is that this Q vector that you have to use to compute the scattering, the differential scattering coefficient and the structure factor here, then the modulus of that is not the vacuum or the background wave vector, but is the background in an effective medium that comes out from the theory. Computing the value of this effective medium might be an issue, okay? But that's the main difference that you have. Okay? So this effective medium is the medium that the average field sees on propagation. So it can be a complex number, so you have to take the real part here, and that changes the way you compute this integral. That's basically the change. You can look at details in several references on this. So this formula has been used a lot to describe experimental results. The way it's established sometimes is a bit hand-wavy. So at least in this paper that hopefully one day will appear, which is a review paper, we have tried to make this clear. All right. So now let's try to enter in more detail a specific case where you have this strong effect of facial correlation, and for that it's nice to discuss this particular case of hyperuniformity. So I was talking about this structure factor that probably you've seen for the first time in your lecture on the properties of crystals and X-ray scattering, and the way you can, for example, get the structure factor by doing X-ray diffraction on a almost here perfectly ordered structure. So if you have a crystal, I mean purely periodic distribution of points, then the structure factor only shows peaks like that, Bragg peaks. So technically, this is a series of delta function that you know, and this gives you the orders of scattering when you send light or waves on this crystal. If you have a completely disordered structure, like an ideal gas, I was telling you that this structure factor for all values of Q, so Q here is normalized by the average distance between particles, okay, so this QA. So it's just one like this would be this dotted line. And in the presence of short range order, then what you get is a structure factor that takes a shape like that. We see the same shape that you would get in a liquid. Okay? If you look at this could be the position of atoms, let's say, or molecules in a crystal. In an ideal gas, you would get this, one. And in a liquid, you would get something that looks like this Schroter factor that sometimes people call a liquid Schroter factor, and that's typically this peak, okay, shows the average distance. So the Q corresponding to this peak is on the order of 1 over the average distance between the scatterers. There is something that could be useful to understand qualitatively why you always get something like that, is that for the structure factor you can derive the sum rule. So there is a sum rule. So this is just the density here. So this integral has to keep the same value, provided that the number of points is just the same. So this means that you see, if if somewhere you increase S of Q above 1, it has to be compensated somewhere by a decrease below 1. So that explains the fact that you always have shape like that, because the integral has to be the same, has to be a constant value. By the way, you see that S of Q equal 1 does not satisfy that, which means it's an approximation. Because an ideal gas cannot be exactly S of Q equal 1, because you cannot put two particles exactly at the same place. So you need a tiny correction, and the tiny correction satisfies this. Okay, but that's, I think, qualitatively something that could be useful to have in mind. Okay? There's no way you can make S of Q mostly above 1 or below 1. You have to get something that looks like this. So what do we mean by hyperuniformity? So this concept was introduced by Torquato. I was about to say recently, but it's almost 20 years ago. Okay. So these are two-dimensional distribution of point patterns. So I guess you can see the S of Q computed from that here. So here it's completely uncorrelated. It's an ideal gas, so you get a kind of blob around Q equals 0. So this is Qx, Qy. Okay, this is the Fourier plane. For a periodic structure, you get the Bragg peaks. Okay, this is just the diffraction pattern of that you see here. But you can have structures for which, although they are disordered, the S of Q here really tends to 0, close to Q equals 0. In the previous slide, you see, you get something like that, but always for Q equals 0, S of Q saturates to a finite value. It's not obvious to get something that really tends to 0. So it can tend to 0 continuously like a power law, or you can even get a particular case for which in a neighborhood of the origin it's really 0, which is called, from reason that will become obvious in the next slide, stealth hyperuniformity. You can understand that at least in the single scattering, it's easy to see that this would kill scattering. So that's why it's called stealth, because you get transparency. So those structures for which S of Q tends to 0 when Q equals 0, I call hyperuniform, for a reason that will become clear in the next slide. But keep in mind that it's not, all structures are not like that. It was, by the way, discovered by chance by Torquato. If you want to get a good introduction to hyperuniform and also the story, I really recommend this review paper. That is very, very nice. Not introduction, but a very nice, deep presentation of the topic. By the way, periodic structures satisfy that. Because between 0 and the first Bragg peak, you don't have anything. Okay? So, but here I will talk about hyperuniformity of structures that are not crystallized, so that are still not of infinite range correlation, like a periodic crystal like this. Okay? So why do they call that hyperuniform? So assume you take here a disk, or in 3D a sphere, and you count how many particles, how many points you have inside the sphere, in the limit where the sphere becomes very large. So if you have an ideal gas, so the points are completely randomly distributed, what you get is that the variance, so this is the variance of the number of points in this large sphere. Okay? The variance is like the average value. This is what you get for a Poisson distribution. Now, in the case of hyperuniformity, so this is the real space version of S of Q tends to 0. Okay? You can derive this relation. What you find is that when you make the sphere larger and larger, the variance grows slower than the average number of points. So it fluctuates less. Okay? So it means that if you zoom out, then the system looks like more and more uniform. So that's why they call it hyper-uniform. And I was telling you that S of q close to 0 tending to 0 means that, at least for small q, you will kill scattering. Here you have the other version, which means, remember the first minutes of my talk, you kill density fluctuations at large scale, which means you kill scattering. Okay. That's completely consistent. So how can you play with this? So first, you can do a lot of interesting things in silico. You can do a lot of numerics. So you can generate hyperuniformity. So this is something I borrowed to the thesis of Romain Monsarrat, did this thesis with Arthur Gucci and Romain Pierrat. So the idea is that you want to generate here in 2D, but you can do that in 3D. You can generate point pattern with an increasing level of hyperuniformity. So in Fourier space, this means that this is S of q again, qx and qy. It means that you want to make S of q 0 in a neighborhood of the origin. So what you can do is that you impose that the integral of S of q here has to be 0. So it gives you like a kind of energy that you want to minimize. And by minimizing this energy, you end up with a structure that shows this nice here high degree of short range order. You can have a measure, so this parameter chi here will appear several times in the next slides. You can have a measure of the degree of hyperuniformity. So typically it's defined as the number of constraints that you impose divided by the number of degrees of freedom. In practice, what this means is that this number is the number of points here for which you impose S of q equals 0, and the number of degrees of freedom here is the number of translation degrees of freedom, so 2 for each particle, minus the global translation degrees of freedom. So you can compute that. This number is between 0 and 1. For chi equals 0, you get a completely uncorrelated structure, an ideal gas. Chi equal 1 is a crystal. Chi equal 0.5 is a transition between something that looks random and something that really starts to crystallize little by little. But you can play with the parameter to get more and more correlated structures, satisfying this stealth hyperuniformity condition. So it's called stealth hyperuniformity. So obviously, we can understand why this leads to transparency, which is very easy to understand. Before that, I just want to show you an interesting scaling that also sometimes is forgotten. So assume you have a material. So again, material for me is an ensemble of scatterers in a transparent matrix that scatters light, and start with a material that is an ideal gas, no correlations. So the mean free path is this. How could you make this transparent, but without adding or removing material? So a way to do that is to break the scatterers into very, very small pieces. I don't know if you're aware of that, but if you do that, at some point you will kill scattering. And it's a very simple scaling, but so if you break the scatterers into smaller and smaller pieces, so you don't add or you don't remove material, so the volume fraction is constant. And the volume fraction scales like the density times r cube. R is the size of the particles. So I make r little and little and little, so I decrease r because I break the particle into small pieces. So you have this scaling, so that shows you that then the density scales like that. But when you do that, at some point, you will reach a regime where r will become smaller than the wavelength, very small compared to wavelength. So the scattering cross-section, which is the square of the probability, you know that in that regime, it scales like the 6th power of the size. So all in all, you get this. 1 over the mean free path scale like r cubed, that tends to 0. Okay? So if you do that, at some point, you kill scattering. Also, you don't add or remove material. This has nothing to do with correlations, but just I think it's nice to see that once in a life, okay? So I was like, where could I put that? Well, here. Now, something that has to do with correlation is that obviously in this formula, if you make S of q equals 0 on the integration domain, then LS will become infinite in theory, and then you will kill scattering and you get transparency. Okay. By the way, what this means, because now if you assume that you have statistical isotropy on average, so S of Q will only depend on the modulus of Q. Q is Ks minus Ki, okay? Seen here. Q depends on the modulus, and the same if you have, let's say, spherical scatterers. The differential scattering cross-section only depend on that. So this integral over the solid angle, you can transform on integral over Q, and you see that Q has to be integrated between 0 and 2 times Kr, which is the K vector in the effective medium. Okay, so that tells you the rule to get transparency, you need this equals 0 for Q between 0 and 2 Kr. So if you take this diagram here, so this is Kx, this is Ky. If you have stealth hyperuniformity in a domain with size K, so this gray region corresponds to S of Q equals 0. So you have the incident light arrow. The length is 2 pi over lambda r, so it's Kr. This is the scattered arrow, same size. And if you want to kill scattering, for all values of Ks, you need to be in this shaded region, which just tells you that K has to be larger than 2 times the length of this arrow. Okay, which is what you see here. So in single scattering, it's obvious that it works, because you probably remember that in single scattering, the scattered intensity is directly proportional to S of Q. Okay? So this is just a numerical simulation showing that. So we start with a completely disordered system with a mean free path. We call it LB. Okay, this is the 1 over rho sigma s. That is larger or on the order of the thickness of the medium. So this is a simulation here. We send light and we look at the intensity around. And so this is the, let's say the scattering diagram. Okay, so this is the intensity versus angle. For uncorrelated structure, then you get a lot of scattering in that case. And for the same density, the same scatterers, but distributed on a point pattern that satisfies this condition, then you completely kill scattering. You reduce scattering by a factor that is the value of S of Q. So if S of Q is really 0, then you get 0. But if it's 10 to the minus 4, you reduce by a factor 10 to the minus 4 in the single scattering regime. In the multiple scattering regime, provided you are in this limit I was telling you that you could, with the diagrams I was showing, okay, you remember you have the paths that go along the same sequence of scatterers for E and E star, or along correlated sequences, provided that these are the two dominating processes, then the formula I was writing works, and then you get that also in the single scattering regime, so the multiple scattering regime. So here, even the uncorrelated structure is strongly scattering. Okay, so this is the red diagram. You see you have a lot of reflection because it's strongly scattering. But now if you distribute the same scatterers, same density on a hyperuniform point pattern, then you completely kill scattering, which is what you expect. So you can get transparency. You move from something like that to something like this, that in practice is reached, provided that LS becomes much larger than the system size. Okay? You don't need real infinity, so you don't need the real S of Q equals 0, but you need S of Q as small as possible in the wavelength window between 0 and 2 times Kr. So for all wavelengths in this window, you get transparency. Okay? But there are many, many other interesting things with hyperuniformity. So, and we'll only scratch the surface of a very active current topic. So the people who introduced this concept, so Torquato and Steinhardt and Paul Chaikin in New York, and maybe many co-workers, also discovered something interesting. So these are measurements in the microwave, is that even a disordered hyperuniform structure, at least in 2D, can show band gaps, which was a surprise. So what you get here are real structures that were fabricated. Okay, this is microwave, so it's easier to make the structures. So you have two different kinds of lattices. Remember that a periodic lattice, is hyperuniform. Okay? A quasi-crystal, which is also hyperuniform, and a disordered hyperuniform structure. And what you get here are transmission spectra. So this is the incidence angle, and this is frequency. Okay, and the color means the level of transmission. So there are transmission spectra through structure like that. And they were surprised to see that even in the disordered hyperuniform structure, you can get a nice band gap. So this has become a very active topic. I will understanding the origin of band gap in non-periodic structure is something that is still not completely understood. So I look at the experts that say, okay, so this is safe. There is another interesting topic that has to do with Anderson localization. That a topic that was introduced yesterday. By the way, I'm happy to see that. I will also speak like an old guy, but now we can talk about Anderson localization in a quite relaxed way. Because for the youngest, I can tell you that 15 years ago, as soon as you would put a slide with this, people would shout, well, I mean, this was really a kind of hysteric topic, you remember. Huh? Okay, but it's still an open issue, as you understood yesterday in the talk of Robin Kaiser. At least one of the open questions is whether light localizes in 3D. I will not enter that. But I just want to show you something that, okay, this was a review paper published some years ago, a few years ago, but these are examples of samples that were used to, let's say, at least claim Anderson localization in microwave, in optics, and with acoustic waves and so on. So again, I don't want to enter the discussion whether this was demonstrated or not. Just want to draw your attention on the fact that even a non-expert would tell you that all those samples are really, really strongly correlated. And it's been only recently that the idea has emerged that the presence of such high degree of correlations might play a role. So that's interesting because that's the way science works. But okay, I hope you agree. But this one is amazing. Okay, but look, even this one. I mean, all of them are very far from the ideal gas, and taking that into account in the theoretical approach is only something that has been done recently. But I think also that the understanding that this was not a detail, but that this could even be the root of the onset of localization is something recent. Okay, so I find it very interesting. So there are people that are very active on that in this audience. So that's, for example, a diagram, a kind of phase diagram for. So I'm coming back to stealth hyperuniform structure in 2D that was proposed by Louis Frufe and co-workers in the group of Frank Sheffold. So what you see here is this chi parameter, okay, between 0 and 1, and what you get here is the frequency. A is the average distance between the point, okay, so it's the normalized frequency. So it was, if I understand correctly, Louis, you correct me, but it was guessed, and then in that paper, checked numerically that this phase diagram makes sense. So I will not enter too much the details, and again, I'm not sure I would be able, but what you find, so this is the stealth region that I was commenting. See, that's the zone where you find transparency. So you expect a zone with band gaps that is surrounded by a zone where you expect Anderson localization, in a kind of mixed regime, and photon diffusion around. So that's very interesting to map this, and I want to stress a very nice experiment from the group in Nice. So Geoffroy Aubry and Fabrice Mortessin are in this room. So that's a two-dimensional experiment in microwave. So I guess you can see the distribution of scatterer here that is distributed on a hyperuniform point pattern, a stealth hyperuniform point pattern with chi equals 0.3. So it's just like going along this line here. And what you see here are maps. So this is an experiment here, it's a real experiment. So what you see here are maps of the field or the intensity distribution, but you can directly map the field in microwave. But what you get here is the different frequencies. And what you do is that you go from here to here. And by looking at the shape and the distribution of the field, you see that you get here. So you see some interferences because it's a cavity, but here you are in this regime of stealthiness, which corresponds to this. And then you move to a regime where you see diffuse propagation, and then localization, and the gap in between where you don't see modes, and then again diffusion. So this is the first experimental evidence that this phase diagram is really something that makes sense, at least in 2D here, and that shows you that there is much more between this concept of hyperuniformity than this transparency I was commenting. So it's interesting to see that this presence of spatial correlation can qualitatively change the picture. Okay, because there are not so many materials for which you would get a diagram like that. Okay, so that's something. So it's work in progress. You see, these are really recent publication, and I also want to stress this work that is the the core of the work of the thesis of Romain Monsara, which is still on archive but should appear soon, or maybe it appeared and I missed it, but no, it's not published yet, right? Okay. So be ready to read that as soon as it comes out. Okay, so that's a very rich topic. So I now want to jump from basic and fundamental stuff to practical, I would not say applications yet, but at least practical way to make things like that. Because you can think about two different kind of approaches. You can think about some top-down engineering, which means you use complex lithography techniques. So I'm showing this very nice work from the group of Frank Sheffold, where by starting by UV lithography in a polymer and with different process, they end up with a connected network of silicon like this, which is hyperuniform, and which shows a nice band gap around, if I remember well, it's in the telecom wavelengths, right, 1.5 microns. So it's the first evidence beyond the microwave experiment I was showing that you could actually see band gaps in structure like that. It's a hard work to make a structure like this. So it's very good for proof of concept, but I don't think that there's hope that one day we will fabricate large-scale materials like this. So another route that is very, very active topic currently in people in soft matter is to try to find some self-organization processes that would not only lead to hyperuniformity, because hyperuniformity is a limiting case, but at least to induce a high degree of short range or even a long range order. There is a very simple idea, maybe it's obvious for all of you, again, I don't know, but is that repulsive interaction induce order. Okay? Repulsion, not attraction. Okay. We've seen that a lot during COVID. I'm sure you've seen that, okay? Even in the metro in Paris, that was funny because even the people flowing in the channels of the metro, I mean, you could see some short-range order because people were avoiding each other, especially in the period where we didn't know how this was transmitted and so on. So everybody was a bit crazy about it, and I'm sure you really saw things like that in practice. These are repulsive interactions. A bit of history. This is an amazing paper. I don't know why if you know about this paper, but because you worked on structural color. But so this paper is very famous in colloid science because that's the first paper. So this is 1986 that showed the so-called glass transition in colloids. So it's a very famous Nature paper. So what you see here are suspensions of glass particles, glass spheres. From right to left, you increase the volume fraction. So so this is again very important in colloidal science because what you probably see better here is that you start with something that looks like something disordered, and then you get a polycrystal, and then people would expect to see a crystal. But then what you see is again something disordered that is technically a glass, and that's the first evidence of the glass transition, which is something that is not completely understood yet. I don't know if you know a bit about that. But that's funny because it's the first paper that convinced people that with colloids, you could get phase transitions that would mimic what you really see in atomic physics. So it's a very important paper on that aspect. These are real colors. This paper does not say a word about the appearance of colors, which is amazing because it means that, I mean, so to my knowledge, it's the first paper that shows an amazing appearance of structural coloration due to short-range order. because look, this green color and this blue color is what people now fabricate and try to understand. This is just pure glass in a transparent liquid. There's no absorption. But it's funny because neither the authors nor the referees were amazed by nobody asked, by the way, why do you see green, blue, and so on? Okay. So this you've seen, okay, but again, you see 1990. So this was the paper by Fradon and Maret. So 1 over the mean free path versus the volume fraction. And this is what you would get for the ideal gas. Okay, so the inverse mean free path would scale like the density or the volume fraction. And then you see that you reduce the mean free path here. So the circles are the measurement, and the line is just this formula that you've seen before. So it's really an effect of the structure factor, but here, due to the fact that when you increase the volume fraction, you start to get art-sphere interactions. So later on, Sheffold and co-workers have shown that you could do a bit more. Because you could, for example, by using a charge colloid, so you can add on top of the art-sphere interaction, you could add electrostatic repulsions, so longer range. And this is again 1 over the mean free path versus the volume fraction. So this is, let's say, the Fradon and Maret curve again, but they could do something like that, which means shaping the 1 over the mean free path, which is the scattering strength, by changing the structure factor because you had another type of interaction. So they introduced with that the concept of photonic liquids. Okay? It's not a photonic crystal, it's like a liquid in which you control the short-range order. And for example, if you look at the diffuse transmission, so it's a strongly scattering material, okay? So the diffuse transmission versus the wavelength, so you see that you can shape the spectrum. Okay, so this is what you get for pure art sphere. And when you add the electrostatic interaction, then because you change the mean free path differently for different wavelengths, then you get this. Okay, so you can shape the photonic properties of a disordered system by playing with interaction. A similar idea was introduced, but in a different way, by the group of Cefe Lopez. At the time was Ricardo Sapienza, that probably many of you know was a postdoc there. So they introduced this concept of photonic glass, which is interesting because the basic idea was you make a monodisperse distribution of spheres, but not crystallized. Okay, so it's monodisperse, so those spheres can have Mie resonances, all the same. It's dense, so the transport mean free path can be very small, but it's not crystallized, which is not easy to make, so they had to set up a process for that. So this concept of photonic glass has been used a lot, and also recently to make new kinds of random lasers and so on. But the basic idea that showed that the interest of it was really that, again, if you measure the average, the diffuse transmission versus the wavelength, or 1 over the wavelength here, then you see that you have some kind of reminiscence of the Mie resonances of the individual scatterers, although it's diffuse light. Okay, so photonic glass. So initially, they introduced the concept the way I was telling it, and without stressing too much the fact that the correlations in position in these glasses would play an important role, and that to describe things like that, you need to account for those correlations. I think now it's understood that these are a class of strongly correlated materials, but still producing diffuse light because you don't have periodicity. And finally, another current trend that is very active, so this is Silvia Vignoni's group, where you can design structural pigments. So the fact that you could get pigment, for example, in paints that would produce colors by scattering is something very important, because people are trying to think about paints that don't use organic solvents, and so that's an active field to see how you can produce that. So one route is to use bio-inspiration. So this is a fruit, and this blue color is due to the short-range order produced by cellulose. So this is just cellulose, this material. And they were able to produce in the lab a blue film like this by a self-organization process that mimics the structure you get in this fruit. So you see, this is really recent work, and this is really oncoming or ongoing research. So that's something you can also have in mind. Now, coming back again a bit to some history. You have photonic liquid on your eye. So maybe you know that, or maybe you don't know, that the cornea and the understanding of the transparency of the cornea has been a nightmare for people doing optics for decades. So this paper, to my knowledge, 1969, is the first who really gives a convincing explanation of why the cornea is transparent. So the cornea is made, your cornea is made of stacks like this. So this is several microns of collagen fibrils. So those fibrils, here you see them in that direction. You see another stack where they are perpendicular to the plane of the slide. So those fibrils are several microns long, and the cross-section is typically 30 nanometers, and it's very monodisperse. So you see it's dense, but it's not crystallized. It's not a crystal, it's not periodic, but it's dense. So if you would assume that this works in the independent scattering regime, so you have a cylinder, typically you know the index of collagen, and it's typically in a liquid that is like salt water, so you can compute the scattering cross-section, and you compute rho sigma s, and you get a mean free path that is smaller than this, and you expect your cornea to be white. So understanding why it's not strongly scattering was done in that paper. So they measured, here it's the pair correlation function. So the Fourier transform of that is this S of Q I've been commenting. And they could compute the transmittance over the visible spectrum. And in the papers, they get a formula. They don't write it this way, but they get exactly this formula. So by the way, it's published in the Journal of Optical Society of America. I mean, I think that today a paper like this would be in Nature, but because to my knowledge, it's the first paper to really explain why your cornea is transparent, and it's a nice application. So you see, it's an old story, but people just forgot that the cornea was a photonic liquid. There is interesting physics, so that's something the late Juan Rosas drew my attention to this a long time ago, that you have the same physics, exactly the same physics and the same formula, to explain the resistivity, or we should say the conductivity of liquid metals. It was not understood until this paper by Ashcroft and Lechner. This is the Ashcroft of the Ashcroft and Mermin textbook that maybe you know. It was not understood why the resistivity of liquid metals was lower than expected, because in a crystal you have bond theory, you understand everything, and then you say in a liquid you just destroy that. There's no periodicity, so you expect the resistivity to be very high. And people were doing measurement, and they would find values of resistivity much lower than the simple calculation of electron transport in a disordered sample. The story is that the ions have repulsive interactions. So actually the electron in the liquid metal see an ion network that is strongly correlated, short-range correlated. Okay? You get a social factor like this. And then the electron sees something that looks like that. And then the scattering mean free path of the electron is much larger than what you would get if everything was uniform. And then this is the same formula for the cornea. It's funny because it's almost the same year, 66. The same physics, same formula for two different things. Okay? So this is all stuff. So this was an overview of current work, a bit of history. And now, in the minutes that remain, I want to show some example of attempts to do interesting materials with correlation for by self-organization. So this was a work done essentially by Pavel Yazgur when he was in Paris, and the attempt was to try to self-assemble droplets. So this is two-dimensional by using a microfluidic channel. Here, what you see are images of assemblies of droplets with two different sizes. So it's a bi-disperse distribution. So you have large particles and small particles, and the fraction of large particle compared to the total number is the control parameter. So depending on this, you can get polycrystalline structures, or you can get something that is random, and that when you plug the structure factor, the spectral function here for bi-disperse emulsion. So you get, so these are really measurements on those structures. For completely amorphous structure, you would assume that for Q close to 0, you would saturate to a value like this, and you see that you start to get something that really shows a trend of going to 0, which is what you expect for hyperuniformity. And with Romain Pirat, what was done is to assume that now, if those would be a two-dimensional scattering material, we could calculate the optical thickness. So we show that the mean 3-pass actually would be increased in the region of parameters here, for which you would get the highest degree of hyperuniformity. So we didn't get. We more or less stopped this because there are at least two drawbacks. One of them is that the size of the droplets here that can be manipulated by microfluidics is on the order of 30 microns. And it turns out that at least a few years ago, it was very difficult, apparently, to find a strategy to reduce the size and get something that would fit the wavelengths of optics. The second problem is that Pavel could not find a real way to stack those things and to do a 3D material, so he moved to something very different. I've seen there is a poster here because now Pavel is in the group of Frank Scheffel, working very actively on new way of fabricate foam that could be of interest for photonics. So I recommend you have a look at that. But this was an attempt to see hyperuniformity. We saw something, but we don't think it's really relevant for real applications. Finding self-organization processes in soft matter to make three-dimensional networks of particles that will be hyperuniform is still an issue, and you have the brightest people in soft matter that work actively on that. I mean, it turns out that it's quite complicated to find processes. I'll show you a second example. So this is not hyperuniformity, or maybe it is, but we haven't seen that. But so this is something we did with Nadine Nassif in the condensed matter chemistry laboratory at Sorbonne University. This is a very interesting material. So what you see here is a material that is 95% water. Okay, and you see that it has amazing mechanical properties, and it mimics an artificial cornea. So technically, it's a collagen hydrogel. So you start with collagen molecules in water, and then you have a process that they could find in vitro that make a kind of condensation of those collagen molecules into fibrils of the type you had in the cornea. So those tubes, 30 nanometers diameter and a few micron length. And then at some specific concentration, they can organize in a network that makes a material. Although it's 95% water, you get something that is a gel that you can manipulate. But the interesting thing that was for them a completely open question is that they could fabricate material like this. So this piece is on the order of 1 centimeter, okay, for which the collagen concentration, you have a gradient. Okay, so it increases from here to here. So it's strongly scattering, but at a specific concentration that they patented, you get transparency. So they came to see us and said, we don't really understand how this can happen, because you can get transparency by changing the density, but it's a kind of monotonic process. You make the things more dilute, or it becomes homogeneous. But then here, something should happen with the microstructure. So the immediate answer was there should be something with the structure that makes this material more transparent. So we make the story short, but we measured that in the lab. So this was done by Jean-Marie Chassot at l'Institut Langevin. We use optical current tomography to measure inside the material the scattering mean 3-pass. So we could show that if you measure at different locations, then the scattering mean 3-pass changes, and that explains this appearance of a much more transparent material, which was something unexpected. So this I can skip. And that's the way it looks. So this is another view of those kind of material. And this is the microstructure. This is 200 nanometers, so this is the nanostructure actually. What you see are collagen fibrils. So we haven't studied in detail, maybe later, because it's not an easy. I'm not able to plot a structure factor or things like that. But at least qualitatively, what you see is that for this critical concentration, for which you get transparency and at the same time very interesting mechanical properties, you see that the collagen fibril arranged in a stack that looks like what you see in a real cornea. The amazing thing is that if you go below or above this critical concentration, you lose transparency, but you also lose the interesting mechanical properties. So for us, interesting because I think it's a nice photonic material. Again, keep in mind that it's mostly water. And for the group of Nadine Nassif, they are also pretty much involved in understanding how self-organization processes could occur in vivo. For example, how the cornea is made in vivo is not understood yet. But it's not that you have a cell that is programmed to get that kind of protein and so on. There should be some self-organization processes behind that. So that's also maybe the fact that this mimics at the end what happens in a real cornea maybe could show that the process they found is what happens in vivo. So it's also ongoing research, not our business, their business, but it's just to put the general context. And I'm lost with the color, but 5 minutes? Okay, good. So that's another example of an amazing material. So this is another soft matter group, Michel Cloître at ESPCI. So they do something different, but that also for us is amazing because it's again mostly water. So they make something that looks like a gel, but actually it's a dense colloidal suspension. But the particles are made of a kind of cage. So this is a reticulated polymer here. So you have a polymer that makes a cage, and inside you have water. So it's like making a water particle, and then you make a dense colloid with those water particles. Well, that's my way of saying it. Okay, but so you see here the different colloids, and you see that you have a high degree of short-range order. So you can measure a structure factor. So these are measurements. But the nice thing is that, look, this is very nice. Those by changing, so this is just the concentration of polymer, okay? So here it's 99.7 water. And in that case, it's 96% water, okay? So this is mostly water, but somehow you structure water and you get this nice appearance of structural coloration. That so you could show how the maximum wavelength, the wavelength of the peak, scales with the peak of the structure factor. And we could, with a very simple model, because they could measure transmission spectra. So this is the ballistic transmission. So this is one of those samples, okay? And you see that this little shadow here is responsible for the appearance of color. And you can describe that very, very precisely with this simple model. And since it's mostly water particle inside a water environment, it's a very, very small index contrast. So we use the so-called Rayleigh-Gans theory to compute these things. So everything is analytical and you can get it. But I mean, I wanted to show you this because I find it very nice because it's mostly water and you get nice color. All right, so this I will skip and say a few words about absorption. Because I was telling you, okay, by starting with a scattering material and distributing the scatterer on a stealth hyperuniform pattern or something that is close to a stealth hyperuniform pattern, then you can kill a scattering. But now the question is, assume you start with small scatterers that are also absorbing in a transparent matrix. If you kill scattering, can you increase absorption and go to something that would mimic a black body? So we actually studied that, so I'm not sure I should go too much into details. No, this I skip. It's a pity, but I can explain after if you have some questions. But maybe just jump to the numerics. So what we did here with Florian Bigourdan and Romain Pierrat was to study the average absorption. So what you see here is the average absorption in a medium like that, normalized by the average absorbed power, normalized by the incident power, okay, versus here a parameter that describes the absorption in individual scatterers. So here we can assume that the density is fixed, the thickness of the medium is given, and you increase the absorption in the individual scatterers. For a hyperuniform structure, so this is what you get, this black curve, and for uncorrelated structure made of the same scatterers with the same density, okay? So you can here just look at the solid line that are numerical simulation in 2D. So what you see obviously is that you increase the absorbed power, the average absorbed power in the medium when you increase the absorption in individual scatterers, but you will saturate to a value because you have a limit that is given by the level of scattering, because everything that is scattered away is not absorbed. So you can obviously think that by distributing those absorbing scatterer on a hyperuniform pattern, then since you will reduce the amount of scattering, you will increase absorption. The nice thing is that, and these were the three previous slides that I skipped, we could even derive analytically that there is an upper bound for absorption, and that with hyperuniformity you can reach this upper bound. Because the physics and the picture you can have in mind is that you try to kill as most as possible the level of scattering, and then this means that light sees a kind of homogenized medium, and then in this homogenized medium you try to maximize absorption. Okay, so you have to do both at once by playing with the level of correlation. So you see that you can get a very large increase. Now, if you divide this by this, then you get a curve like this. So this is what you get for different optical thicknesses, and what you see that so this is the enhancement you get in the absorbed power when you move from an uncorrelated system to a hyperuniform system. So you see that you can enhance by a huge factor. So we could even show theoretically that the maximum enhancement appears for an absorption optical thickness that is a bit larger than 1. Okay? So again, the picture is that you kill scattering, and then light enters, and you want light to be absorbed because it goes to the other side. So you need a thickness that is a bit larger than the absorption mean free path. At the end of the day, the picture is very easy, okay, but to understand, but this is what you get. And you see that the factor can be huge. This is not a tiny effect. Okay? So we could even get an estimate of the absorption enhancement that scales like the square root of the scattering optical thickness of the disordered structure. So if you start with a structure whose optical thickness is on the order of 10, then the enhancement is the square root of 10. If it's 100, you can expect an enhancement of the order of the square root of 100, which is 10. So okay, that's the scaling you get, just to convince you that it's not a tiny correction. You can change the story. The interest is that it's not coherent absorption, which means that it's not resonant, so it can be broadband, and it's very robust. Again, this is the enhancement of the absorption, so it can be very robust against the incident angle because it's an enhancement of absorption in the multiple scattering for diffuse light, let's say. Okay, so you can expect to get something that, at the end, would really behave like a black body. So we have, I have made the story very short, but okay, if you want to look at the detail, you have those papers, and I want to also to put forward those papers that. And especially this one that really shows for thin films the fact that by reducing scattering with hyperuniformity, you can really increase absorption. So if I may use 2 minutes, yeah, because this, let's say it's a kind of conclusion, because the question could be, so what? Okay. So because I want to answer the so what, I have, I think, 3 slides just to show you ongoing work. What could we do with this? There is an interesting topic currently that has to do with this concept of passive radiative cooling. So what you have to know is that if you put a surface under sunlight here, so of course, if the surface absorbs sunlight, it will heat up. But you have a cooling process that you may know that the atmosphere is transparent in this wavelength window. That's why it's very cold at night in winter, okay? Because during the night, you know that at room temperature, the black body spectrum is peaked at 10 microns. So you have a lot of thermal radiation that can go through the atmosphere and live in the intergalactic space. So you have an efficient cooling process, provided that you have a material that emits a lot between 8 and 13 microns. So that gave the idea of this passive relative cooling. Even, of course, at night it's okay because you don't have sunlight, so you have this cooling process. But the idea is, could we get a cooling regime even under sunlight? And the answer to the question is yes, provided that you could get a material that would reflect a lot over the solar spectrum, which is like a black body spectrum centered at 0.5 micron, and that would emit a lot. And thermal emission is like absorption. So if you absorb a lot, you emit a lot. So you need to make a material that is a strong reflector for sunlight and a strong absorber or emitter in this window of the atmosphere. So there are a different way of doing that. There is a company that sells a system that is made of glass sphere. Glass is strongly absorbing between 8 and 13 microns. So you could say, okay, you can make a material with glass that is a strong emitter, and behind that they put a silver mirror. But we came with the simple idea to say, but glass can do everything by itself because glass is highly scattering in the visible, provided you structure glass to make a strongly scattering material. So we are not playing yet with tuning the correlation, but that could be an idea because we could play with correlation to make sure the material is as strongly scattering as possible for sunlight and as absorbing as possible in this 8-13 micron window. So we're not yet in this optimization process, but I just want to end up by showing you that by taking a stupid glass filter, that's something that Yannick de Wiel, who is working on this, who is very smart, found. You can buy glass, it looks like paper, but it's glass filter used for particles. So we took a glass filter like that, such that the thickness was large enough so that you get a strong scattering. And we did measurement, and we showed that in the visible part, the reflectance is very high because it's a strongly scattering material, but maybe we could even tune it to a higher degree of reflectivity by now adjusting the parameter. And at the same time, it has an emissivity. So one would be just like the black body, but it has an emissivity which is very high in the cooling window. So we did those measurements. Yannick de Wiel did the measurement in the lab. So that's really ongoing stuff. But we could estimate that with a material like this, again, that is not optimized for that, but it's just glass. So we have a project with Saint-Gobain now to work on this, because we could expect a cooling power on the order of 90 watts per square meters, which is very nice order of magnitude for people interested in this business. By the way, I should tell you that our measurements show that the performance are much better than this thing that is sold by a startup company. So that's really promising, and that's the end. So this is a take-home message that you can take. Really keep in mind that it's a powerful degree of freedom. You can do a lot of things, and not only adjusting some parameters. You can change the story, change the transport regime. You can get fancy photonic application after that. Self-organization processes are, I think, really important on the route to the production of real materials. And you can revisit basic concepts like the appearance of band gaps or the existence or not of understand localization. And if you want to know more, this is a review paper that should be published soon in Reviews of Modern Physics. And I took at random one of the good textbooks you can find. And thank you for your attention.